Okay, so we're going to start by talking about a polynomial, and the first question we have to ask is, what is a polynomial? And a polynomial is either a monomial or the sum of monomials. So if we remember what a monomial is, it's either a number, a variable, or a product of those things. So something like 4x, that's a polynomial. Something like 4x plus 3x squared, still a polynomial. Minus 5xyz, still a polynomial. So this could be a polynomial. Things that are not a polynomial would be something like 4 to the x. When that x is in the exponent, that's where you have a problem. You can also not have something like x to the negative 2. We can't have that. You also can't have something like the square root of x. X cannot be a radicand. So the exponent must be a positive whole number, and x cannot be a radicand. So these are examples of not polynomials. Oops. Okay, so we are entirely more concerned with polynomial functions. So a polynomial function is just a function that can be written as a polynomial. So something like 2x squared plus 7x minus 3x to the third plus 5 plus 2x to the fourth. That's an example of a polynomial function. Standard form, we'll go ahead and talk about that one, is that the highest exponent is first, so the exponents are in decreasing order. So if we needed to write our function that we have listed as a polynomial function, we're just going to change it so that our exponents are in the correct order. So this function up here can be written as the highest exponent would be this 4. So 2x to the fourth minus 3x to the third plus 2x squared plus 7x. And then plus 5, because 5 doesn't have a variable on the end. When you are in standard form, the degree is really easy for us to find, but the degree is just the largest exponent. So in our case, the largest exponent was 4. The leading coefficient is the coefficient of the term with the highest degree. So here is our highest exponent. The coefficient of that term is 2. And the constant term is the term that doesn't vary, so the term that has no variable. And in our case, that's 5. So we can now talk about our degree, our leading coefficient, our constant, and we can also put our polynomials in standard form. So we've got that, and we also are able to tell when something is or is not a polynomial. I don't know what happened to those. There we go. So when it is a polynomial, it's just the sum of monomials. It's not a polynomial if one of these things happen. So that's our way to test if we have a polynomial. So the end behavior of polynomials. There's two different types of degrees. You can either have an odd number degree like 1, 3, 5, 7, 9, 11, etc. Or you can have an even degree like 2, 4, 6, 8, 10, 12, etc. So the easiest function that we have with an odd degree, our most basic odd degree, would be something like y equals x to the first. That's a degree of 1. It's the odd degree. So our end behavior is going to either look like y equals x or y equals negative x. So if we remember what y equals x looks like, and y equals negative x looks like, we've got our two functions listed. End behavior is just what happens on each end. So in the middle, you don't know what things are going on. It could be anything. So, for example, an odd degree could have an end behavior like y equals negative x, and in the middle you could have all kinds of stuff going on. But we don't care about what's going on in the middle. We only care about the ends. So our end behavior is going to be pretty easy for us to do. So we can start off by saying, for these top ones, that leading coefficient is positive. So if your leading coefficient is positive and you have an odd degree, your end behavior will always be the same, and it's always going to look like the end behavior of y equals x. So if you have a positive leading coefficient, your end behavior will look like this. And it's good for us to have that little picture, even if we don't write it down, as long as we have it in our head. Because what we're going to do to write our end behavior, this little picture is not going to be good enough. We need to actually write a statement describing the end behavior. So if we said as x goes to, if we're going to talk about the left side first, because we read from left to right. So if we're going to talk about the left side, that's this side over here, x is going on and on forever towards negative infinity. So as x goes to negative infinity, we want to know what our y values are doing. And our y values on the left side are going down towards negative infinity. And we do the same thing for the right side of the graph. So as x goes to, in this case, x would be going on and on forever to positive infinity. Your f of x values are going up forever towards positive infinity. So that would be your end behavior if your leading coefficient is positive and your degree is odd. The second one's going to show up if your leading coefficient is negative. So if your leading coefficient is a negative number, your end behavior is always going to go like this. It's going to fall. And so for this one, we're still going to split it up into the left side and the right side. We're going to say as x goes to negative infinity, that's where x is headed, the y values are headed up towards positive infinity. So if it's going up, you're going to be going to positive infinity. And for the right side, x goes on and on forever towards positive infinity. And as x does that, on the right side, our y values are going down to negative infinity. So up is a positive infinity, down is a negative infinity. And that's odd. That's the only kinds of end behavior you can have for odd degree functions. So even degree, our most basic even degree would be x squared. And we just got through talking about quadratics. And for that, you either have a positive x squared, which opens up, or you have the negative x squared, which opens down. And again, we don't care what's happening on the end. You could have something like this with the end behavior, and it could do all kinds of crazy stuff in the middle. But we only care about the ends. We don't care about any of that. We just care about the ends. That's why it's called end behavior. So if we're going to look at this top one, again, that's for a positive leading coefficient. So if your leading coefficient is positive, our end behavior is still going to be split up between the left side and the right side. And we talk about the left being x's going towards negative infinity. And we talk about the right being x's going towards positive infinity. So on the left side of our graph, our y values are going up. So we would say f of x goes to positive infinity. It's going up. On the right side, our end behavior is that our graph is going up. It's going to positive infinity. And that's it. That's our end behavior. So we do the same thing for a negative x squared. So for the leading coefficient being negative, your end behavior looks like this. So we still split it up with the left and the right. So as x goes to negative infinity and as x goes to positive infinity, negative infinities on the left and positive infinities on the right. So we start the same way. On the left side, our y values are going down. They're going towards negative infinity. And as x goes to positive infinity on the right side, our y values are going down. Same thing. So if you notice the difference between the evens and the odds, the even degree end behavior is the same. Meaning that these two things here are going to match. So your end behavior will always be going the same way. For odd degrees, your end behavior will always be one up and one down. You're never going to have both going the same way if you have an odd degree.